Welcome to another unit in the workbook Statistics. This time I'm talking about the exponential distribution. The exponential distribution can be used in two situations, or is mostly used in two situations, and it's a continuous distribution. Well, what are the two situations where they are used? Well, in those where the entry probabilities increase or decrease exponentially. So we can imagine the density function being an exponential function. Or, and that's also something like a nickname for the exponential distribution, it's called the distribution without memory. So the probability of one event happening is absolutely independent of how often or when an event has happened before. So the past does not matter for the present. For example, if we say, well, the shutdown time, so until a computer will shut down due to an error, is exponentially distributed. This means it doesn't matter how long the computer already has been running. It still has the same probabilities as if you just switched it on. That's the main idea behind the exponential distribution. Well, what about the density function? As I said, the density function is something of an exponential function. We see here a negatively developing exponential function, and we have a parameter lambda here, which details how the density function actually looks like. If we have this density function, well, it's relatively straightforward in calculating the respective distribution function, which then looks as follows. So we have the density and the distribution function in closed form, so we can easily calculate probabilities for the exponential distribution. We do not need, as for example with the normal distribution, a particular type of table to look up the values for the distribution function. Also, one comment, due to the factor lambda, and why we're going to see in the next slide, the exponential function in some cases is related to the Poisson function. And yes, they actually have some similar properties. They're not perfectly the same, but well, it's similar. If we take a look, here we also have, as a general idea, the density function for different exponential functions depending on the parameter lambda. So here we can see the differences for values of 1, 1/2, and 4. So it's getting steeper here if lambda is actually increasing. Well, as I said, it's similar to the Poisson distribution, so lambda tells us also something about the relevant statistics for this distribution. But first, let's go to the probability. The advantage, we can directly use the distribution function to calculate probabilities of the classical nature we're going to work with when we work with continuous distributions. So the probability of a variable being smaller or equal to k is nothing else than k being inserted in the distribution function of the exponential distribution. There's one other aspect, that's more or less the nature of it not being impacted by past events. So if we want to have some kind of conditional probability, we can skip this conditionality here. So it's not impacted by conditions which more or less are of a timely nature. And as I said, we have some central statistics, being the arithmetic mean, the mean of the distribution, and the variance, which are closely related to the parameter lambda. Here we have the average as 1 divided by lambda and the variance as 1 divided by lambda squared. Or in other words, the standard deviation being 1 divided by lambda. And that's why it's, well, often related to the Poisson distribution, because here the mean and the standard deviation are the same. Well, they're not directly similar to lambda, but we could simply write lambda in a different version and we would have the equality of mean, standard deviation, and the parameter of our function. Well, that's then everything there is, everything I wanted to mention regarding the exponential function. So I hope you enjoyed this session. I say goodbye and see you next time.